right? And then the last one, intuitively speaking, the height of the last rectangle should be whatever f of 1.9 is, and that works out perfectly. Okay, so I think we're ready to go. Oh, and Robert Rose, anticipating what I was going to do next. Wait, can you, no, don't math bracket, because it's going to be nothing. Robert Rose, anticipating what I just asked for, has just done that same thing that we just did a minute ago, 1/10 sum of the sequence of the blah, 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 and now all you had to do was change it from 0 to 19. So you could even do like, what's that called? Like second entry, and you could like punch up the old one. You guys know what I'm talking about?
Yeah. Second entry.
If you use second entry, it like brings up the previous things. Okay, and if you do this, you get this thing that we call L20, and I believe Robert Rose did it right. He got 13.954. 9541. We'll give everyone a minute to catch up. Can you look up when you have successfully entered all this into your calculator and you got the same answer I got? Are you cool? We're almost there.
Mr. Rose,
Go.
I make a hypothesis.
Yes.
If we average the two in some weighted fashion.
So yeah, okay, hold on, pause on that. I want to make one thing I would like to just say right now, which we know. It's standard to kind of to call the integral I. So let's let I, if we let I be the integral from 0 to 2 of e to the x squared dx. There's one thing I can say now for absolutely sure, which is that the true answer lies somewhere in between 13.9541 and 19.3139. Is everyone cool with that? Of course you are. All right, now, by the way, if my function was decreasing, then we would do it the other way, right? If the function was decreasing, then LRAM would be an overestimate, RRAM would be an underestimate. Okay, so Robert Rose wants to do some things. He wants to average them. Now, averaging them might be a good idea, or it might not be a good idea. It really depends on the function. While that's a good idea-ish,
No, it's going to get you closer to the end.
probably going to get you closer, but who knows? Maybe not, right? Maybe the true answer is, okay, pretending I don't know that, maybe the true answer is like 18.5, right? I don't have any real solid math which tells me that it should be somewhere between.
I wager
You
that
do?
there's some way of,
He wagers. He wagers that the average is related to. Okay, before we get to various wagers, what's one way I can make this better? How do I make this better?
More rectangles.
Yeah, more rectangles. Okay, I'm about to say something like really important now. Yeah, with more rectangles, I can do it better. So let's try n equals 200. If I do n equals 200, then what's delta x?
1 over 200.
I think it's 1 over 100 now, right?
Yeah.
Because the width of the thing is 2. Okay, I'm gonna get this one. So let's do so yeah, I know that's very important. So let's go second. If you keep hitting second, whoa.
You're doing answers.
Yeah, I got it. Second entry, it'll bring up old things. So let's do that one. So here we go. This was 1/10 sum sequence, and I need to change this. If delta x is now 1/100th, I think I can just use all my old logic, but I can just make it 100 instead, right? And then instead of that, I make that 100, and now I go from 1 to 200, right?
You're 1.
I think that's right, yeah?
Yeah.
Could someone check my logic pretty quickly? Yeah, I'm going to increment now by 1 over 100. My delta x is now 1 over 100, and I have 200 rectangles.
We got 10 times more accurate.
Are you excited?
Yeah.
Okay, John Park, can you grab the black marker and can you write this following number? By the way, it's taking a long time, isn't it?
Yeah. But it got 10 times more accurate.
It might, oh.
Anyway, and we got 16.722. That's going to be an upper bound, right, John Park?
Yeah.
That's going to be, okay, just trying to encourage you to, whatever. That's going to be an upper bound because that's RRAM. And now, let's find a lower bound. How should I do that? Bring up, or I could just change this. Everything's the same except for
Last thing.
0 to 199. And hit enter. Again, wait a pretty hell of a long time.
Well, that's because that thing is
Wait.
running like.
I know. It's doing lots of horrible things, and we get that. Okay, so calculus tells me that the true area must be somewhere between those two. Jabbar, can you write me a nice little inequality in a box, kind of just like how I did above, saying that the true integral I is somewhere between 16.186 and 16.722. All right, guys, we need to have a deep conversation now. I did just make, if my goal is to find out what this integral is, do you agree that I just got much, much closer to finding it, right? I have now narrowed it down to a band of about 0.5. So, Yanni, I call that progress. But what did I have to give up for that progress? A lot of time, right? This took my poor, sick, old calculator like a good, 20 seconds or something like that, right? And, all right, even if you did this on a modern computer, it would take, some significant amount of time, like a second, which in 2014 is like a million years, to do this. So you're giving up processing power. It's taking lots and lots of computations. By the way, Robert Rose gave us a preview, but he was mumbling, and maybe you guys didn't hear. What if I now said, all right, I did pretty well with 200. Now let's try 2,000.
Consider not overflow.
Well, if I let n be 2,000, then delta x is going to be that, and then this is going to be that, and then I'm going to start at 1, so I'm doing RM now, and I'm going to go to like 2,000, right?
2,000 overflows.
All right, so based on the logic of what I have just done, this should give me an even more accurate answer. But what is going to happen? Now we explode the box. I'm pretty sure it is just going to crash. It's either going to run forever or it's going to crash. That's because this is not just a little bit harder than the previous one. This is like 10 times harder. Not even, there's also a whole thing which I've been ignoring this entire time, which is how the hell the calculator computes e to this stuff anyway, right? There's a whole nother process, which is also has to do with calculus, of how your calculator does this. Okay, let me just turn it off. Let me just break it before it actually solves it and therefore ruins my lecture. But can we confirm that this is taking like at least 40 seconds or so, right? And I think it just won't work. So yes, it is possible that there might be some bigger and bigger computer which is doing better and better. But even if this would somehow have worked, I still would have only got it accurate to maybe like a 10th or something like that. But Arthi, there are times when I might need my answer to be accurate to like 3 decimal places or something like that. So this method sucks. This is kind of subtle here, but because you guys are kids, you just think of all computers as being infinitely powerful and all that kind of stuff. But if you ask it to do more and more and more rectangles, the problem just gets computationally harder and harder. And there's one other difference. This is very subtle. This is something that no one usually talks about except for serious computer science people. What is the other problem with adding up lots and lots and lots and lots and lots and lots and lots of tiny numbers?
Floating point.
Yeah, do you guys talk about that in comp sci a little bit?
Well, not really. But
Not really. Okay, so there are problems, right? There are problems that get down into the very way in which these things are implemented. And the answer is that when you do this, you have all this kind of like floating point arithmetic crap, right? And you have to worry about where the decimal points are. And the point is, every time your calculator does a calculation, it rounds a tiny bit. And normally you don't think of that as being a problem. But if you're trying to do like 2,000 of these subintervals, then the numbers that you're adding are so incredibly tiny, and you're adding so many of them, that the rounding error starts to become actually significant. And what you actually end up with, you end up in this cycle where the numbers that you're adding become more or less garbage, right? Because the error that's involved in your rounding and the way that rounding accumulates, it actually is greater than the number of decimal places you're looking to make your answer accurate to. Are you guys with me? All right, this is a floating point thing. Theoretically, there's this class called, what's our class called that VAM teaches?
Origins of maths?
No, not Madsen, the other one. Computational methods. There's theoretically this class called computational methods that FAM teaches, wherein you investigate these exact kind of problems. How programming languages deal with this problem of like rounding and crap like that. Okay, so what can we do? What can we do? We need something which is better. What can we do? Well, this is already is numerical integration. We've seen that there's another method which we've seen so far in this class, which does better than LREM or RM, intuitively speaking.
It's the middle round.
The middle RAM, yeah. The so-called midpoint rule. The midpoint rule, or you could call it MRAM, but I'm not sure anyone actually calls it that. All right, so here's our new idea. Our new idea is use midpoints. Oh man, we're running out of time. So how do you do this? Well, you have a picture, and you have a picture. Here's 2. Here's a little bit of this. All right, now we're going to partition this up into. Can I look at the blue marker behind you? I partitioned this up into subintervals again. And now, however, so this is still like 1/10, this is 2/10, this is 3/10, etc. But now, for each one of these subintervals, I let my rectangle be the value of the function at the midpoint, right? Say right.
Right.
All right, and just by eyeballing it, that seems to be way, way better than either LRAM or RRAM. And then the last one will be, so if this last one is like 1.9, then the last rectangle will have height like 1.95, right? You guys following all this? All right, I'll take that as yes. Okay, so same problem. I would like to know approximately the integral from 0 to of e to the x squared, and I would now like to use the so-called midpoint rule. Well, delta x is still, the width of each subinterval is still 1/10. Can somebody give me the formula?
Negative 0.5 6 over 10. If we're going from 1 to 20.
Yeah, maybe it's actually just easier to go from 0 to 19. I think that's
Negative 1/5. Never mind. Not negative 0.5.
Yeah, he says, look, where's the first rectangle going to be? The first rectangle is going to be f of 1/20th,
Okay.
right? The first rectangle is going to be f of 1/20th. So this is going to be basically like f of 1/20th plus I over 10. This is a little bit tricky, but I think maybe it's not so tricky. I want to go from 0 to 19. If you have hiccups, hold your breath. It'll go away. Yeah, so do you guys see what Peter Ho just did? And plus me together? He said, all right, look, this is a bunch of rectangles. How many of them? 20 of them. Let's start counting at 0 and stop counting at 19. The width of each rectangle is going to be 1/10. But the height of the rectangle is now going to be kind of like offset by 1/20th. John Parks is okay? It's not so hard, right? Yeah, and then just let's double check it. What's the last rectangle? If I plug in 19, what should the, if I plug in 19, then I get 1/20th plus 1.9. 1/20th is like 0.05. So that last number will be 1.95, which is what it's supposed to be. Okay, let's do it. Did you do it already?
Yep.
Yeah, Robert Rose already entered it into his calculator using the same command, 1/10 some sequence, blah, 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 and we get 16.3622, which is remarkably close to what we have cheated and know is the true answer over there. So,
Good as LRAM.
I'm feeling pretty good about it. What's up?
LRAM is better.
What do you mean LRAM's better?
Oh, 3.6. Sorry, I thought. Never mind.
16.3622, but also this is with n equals 20. So it doesn't make, it's not fair, you like to compare it to when we did LRAM with 200 or whatever. Okay, so we have a name for this, we call this M20. And M20 is simply the answer that you get from estimating an integral using the midpoint rule with 20 subintervals. Everyone okay with this?
Yeah.
Yes, but there's more.
Yeah, there is more. I would, since we are allowed to use any point, any height, or like, we can use any point between, like, right, we can use like a different midpoint.
Okay, I'm moving on. Sorry, I'm running out of time. You're rambling.
Alright.
All right, a new rule, the trapezoid rule. The trapezoid rule says, why are we just sticking to rectangles? What's so special about rectangles? Let's use trapezoids. They are better. So, let's go all the way over here to 2.
Oh, the derivative!
Oh, what are you talking about?
The
So,
derivative of like the midpoint. We use that as a slope in the top of the trapezoid.
I think you're saying some actual smart things, but I'm still going to ignore you because I'm trying to do this. So what we're going to do is same interval, same area, same number of subintervals. I'm still going to let n be 20. Delta x is 1/10. And so there's 1/10. There is 2/10. There is 3/10, etc. But this time, this is really exciting, guys. This time, what we're going to do is, I'm going to plug all these numbers into the function, and I'm just not even going to draw rectangles at all. I'm going to draw trapezoids. And I just connect, right? So just connect. 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 Oh, so beautiful.
Object, like,
So beautiful.
Oh.
Is this making sense?
Yeah.
This last one will be like 1.9. How's it cheating?
It's just a better way. Go be backwards now.
Right. Ooh, is that a backwards rectangle pun? All right.
I don't know how you got a funnel.
Good. Because we talked about anyway. All right. So good. We have trapezoids. All right. Now I was planning on doing a remedial 2-minute lesson on finding the area of a trapezoid, but we don't have time for that. Can I just skip that? We know how to do this, right?
Yeah.
Okay. Good. All right. How do you do this? It's the average of the bases times the height. All right. So what is the area of that first trapezoid? Well, it's going to be the bases are f of 0 and f of 1/10 over 2 times what's the height of the trapezoid?
1/10.
It's like the distance between the bases, it's 1/10. Okay, and then the second trapezoid is going to have area f of 1/10 plus f of 1/20 over 2 times 1/10. Is this all making sense?
2/10 or 1/5.
What happens?
F of 120.
Oh crap. Sorry. 2/10. And then the next one is going to be like f of 2/10 plus f of 3/10 over 2 times 1/10. Okay, and then let's skip to the last two. What are the last two going to be? What's the or maybe we just go right to the last trapezoid. The last trapezoid will be f of 19/10 plus f of 20/10 over 2 times 1/10. Okay, so I am noticing something nice here. What's one thing I'm noticing?
You're dividing by 20 on top.
Yeah, first off I can factor out a 1/2 because they all have a 1/2. Second of all I can factor out a 1/10 because that's like delta x, right? And then basically what am I left with? I'm left with a whole bunch of y values, but I have one f of 0, but then I have two f of 1/10, right? Is that right?
Yeah, right.
And then I have two f of 2/10. And so this becomes f of 0 plus 2 f of 1/10 plus 2 f of 2/10, all the way up to, there are going to be 2 of these f of 19/10 plus 1 of the f of 20/10. Is this making sense?
Yes.
Mary, are you with me? Okay, time to do it on my calculator. Here's the cool way to do this, and I guess this is how far we're going to get. I'm kind of sad. All right, so watch. First, I'm going to construct the sequence which skips by the appropriate amount. So the sequence I'm going to construct, I'm going to do this with, let me just clear all lists temporarily. Or let me clear all lists. And now here's what I'm going to do. I'm going to go sequence. And I want my sequence, I want it to start with 0. So I'm just going to write it as x over 20, comma, x, comma, 0, comma, 20. So this is going to be 21, this is going to just make a sequence with 21 points, which skip by, did I mess this up? I think that should be x of, shouldn't that be,
1.
oh yeah, that should be x over 10, right? Yeah, sorry. X over 10. So I wanted to skip by 0.1 each time. Yeah, sorry. So skipping by 0.1 each time, and then the last one should be 2. Does everyone agree that I've done that correctly?
Yep.
Okay, good. Now what I'm going to do is I'm going to store that in L1. All right. Now I go to Stat, Edit, and I look at L1, and sitting in L1 are all of my various places where I'm going to take sample points, right? Say right.
Right.
And I should have 21 numbers because I'm starting at 0 and ending at the 20th one. Okay, now in L2, I'm going to plug all of those into my function. So I go Enter, I go put my cursor on the L2, and you go vars, yvars, function, y1 of L1. You guys remember this crap from last year? 30 more seconds. So now what that does is it plugs each of those x values into the function. Now I go to L3 and I need to make kind of like a table of weights. So I want the first guy gets once and the next guy twice. And all of these should be 2s except for the first and last. Okay, then I go to L4, and in L4 I take the product of L2 and L3. So L2 times L3. Is this making sense? And now in L4 now is all of these. It's all of these guys basically. And now finally, what do? I take all of that and sum it up. So I go math the sum of L4, and then I still need to multiply by 1/2 and times 1/10, and that gives me the so-called T20, and T20 is 16.634. Cool?
Wait, is this called RTAM?
It doesn't have a name. It's just called the trapezoid rule. You could call it TRAM or something. That's just weird because it's not rectangular anymore. What do you want to call it? TAM?
RTAM.
Triangular approximation.